Welcome to the deep dive. Today, we're diving into some pretty fundamental concepts in discrete mathematics. Think sets, logic, proofs, and even a bit about Alan Turing and how Google got its start. You provided us with some excerpts from a text that looks like a real gem for understanding these core ideas.
It's going to be exciting to see how these seemingly different areas all connect in fascinating ways.
Yeah, I know you're eager to gain knowledge efficiently, so we'll make sure you leave this deep dive not just with a bunch of definitions,
Yeah.
but with a genuine grasp of how these ideas connect and why they matter. Get ready for some aha moments. Let's start with proofs. They're often called the heart and soul of mathematics. Can you explain why they're so crucial?
Proofs are how mathematicians move beyond intuition and hunches to establish rock-solid truth. They require absolute precision and clarity in how we express mathematical ideas. It's not enough to just have a feeling that something is true. You need to be able to demonstrate it logically, step by step.
The source material I was looking at really emphasizes the need to avoid any ambiguity. It talks about how mathematicians use logical formulas to express propositions in a very precise way, kind of like a special language, right?
Exactly. One of the most important concepts in this language is the idea of P implies Q. It's the foundation of so much mathematical reasoning, but it can be a bit tricky to wrap your head around at first. P implies Q is considered true even when the hypothesis, that's P, is false. This often trips people up because it seems counterintuitive.
Yeah, I remember struggling with that one too. Why would a statement be considered true if its starting point is false? That doesn't seem to make sense in everyday language.
Think of it this way. P implies Q is essentially saying if P is true, then Q must also be true. But it doesn't say anything about what happens if P is false. In that case, the statement doesn't make any claim about Q, so it can't be considered false. Imagine I said, if it rains tomorrow, I'll take an umbrella. If it doesn't rain, I haven't broken my promise, regardless of whether I take an umbrella or not.
Okay, that example actually makes it click for me. So it's more about the relationship between P and Q, when P is actually true. The source also has some interesting examples that help clarify things. It also delves into different patterns of proof, like proof by contradiction and proof by induction. Can you tell us more about those?
These are different strategies for building a solid logical argument. Proof by contradiction is kind of like a detective's approach. You assume the opposite of what you're trying to prove, and then show that it leads to an absurd or impossible conclusion. This demonstrates that your original assumption must have been wrong.
So you kind of corner yourself into the truth by showing that the opposite is just ridiculous, right?
Exactly. And proof by induction is a bit like a chain reaction. You prove a base case, which is usually the simplest instance of what you're trying to prove, and then you show that if it's true for any given case, it must also be true for the next one. This creates a chain of logic that extends to all cases.
The book uses a domino analogy. You knock over the first domino and the rest fall in sequence. They also had some great tips on writing good proofs. It struck me that it's similar to writing good code clarity structure, and anticipating how someone else will read it are all key.
Absolutely. In both cases, you're communicating a complex idea in a way that's clear, unambiguous, and convincing. Whether you're proving a theorem or building software, you need to be able to think logically and express your ideas precisely.
So proofs are all about rigorous logical thinking. What's next on our deep dive?
Let's shift gears to sets, which the source describes as the building blocks of everything in math. They're fundamental to how we represent mathematical objects.
Okay, I remember sets from school. They're basically collections of things, right?
That's right. And there are basic operations you can perform on sets like union, intersection, and complement. Union combines elements from two sets. Intersection finds the elements they have in common. And complement identifies everything outside a particular set.
Right, those all sound familiar. But then the book goes a bit deeper with this concept of cardinality, which sounds a bit more complex. Can you unpack that for us?
Cardinality simply means the size of a set. For finite sets, it's just the number of elements. But things get really interesting when you start talking about infinite sets.
Hold on. Different sizes of infinity. How does that even work?
This is where it gets mind-blowing. Cantor's theorem shows that the set of all subsets of a set is always larger than the original set, even if the original set is infinite. So there are different levels of infinity, some bigger than others.
So it's not just that infinity goes on forever, there are different magnitudes of foreverness.
You got it. And this idea has huge implications for computer science. Sets are used everywhere in computing. Think data structures, databases, algorithms. Understanding how sets work, including these infinite ones, is key to designing efficient systems.
Okay, so we've gone from the precision of proofs to the mind-bending vastness of sets. What's next on our journey through discrete math?
Let's delve into the world of logic, the formal language of reasoning that underpins everything we've discussed so far.
Logic feels like something we use every day, even if we don't call it that. How does it fit into the bigger picture of discrete math?
Logic provides the rules and framework for manipulating and analyzing mathematical statements. It's what allows us to construct proofs and build arguments that are not only convincing, but also completely airtight.
The source breaks down the basic logical operators. And D or not MB implies these are like the verbs of our logical language, right?
That's a great way to think about it. And just like with any language, understanding the grammar is key. Logic also uses truth tables, which are like visual maps of how these operators work. And then there's the concept of logical equivalence, which is about recognizing when different statements essentially mean the same thing, even if they're expressed differently.
The book also points out a fascinating connection between logic and sets. De Morgan's laws, for instance, apply to both propositions and sets. But they're not exactly the same thing, are they?
That's a crucial distinction. It's easy to get tripped up by the similarities. While both sets and propositions use similar-looking operations, they're operating on different kinds of objects. Think of it this way. Sets are about belonging or not belonging to a collection, while propositions are about truth or falsity. So even though De Morgan's laws have similar forms, you can't just swap sets and propositions willy-nilly.
Okay, that helps clear things up.
Right.
So it's not just about memorizing formulas, it's about understanding what those formulas represent in different contexts.
Yeah.
Why is logic so important for someone who's not necessarily a mathematician?
Logic isn't just for mathematicians, it's the foundation of computer programming. Those logical operators are at the heart of how code works. Understanding them helps you write better, more efficient programs. But even beyond programming, logic helps you structure your thoughts clearly, analyze arguments, and make better decisions in all aspects of life.
So mastering logic can make you a sharper thinker and even a better programmer. I like where this is going. What's next on our discrete math adventure?
Let's explore a concept called induction, which the source describes as a powerful tool for proving statements about natural numbers. It's like a mathematical domino effect.
Okay, I'm intrigued. How does this mathematical domino effect work?
Induction is a specific kind of proof that works by establishing a base case, the simplest instance of what you want to prove, and then showing that if it's true for any case, it must also be true for the next one. Think about climbing a ladder. If you can get on the first rung and you know you can always reach the next rung from where you are, then you can climb the whole ladder.
So you're not proving every case individually, you're proving the connection between them. The book also mentions something called strong induction. How does that differ?
Strong induction is like a supercharged version of regular induction. Instead of just assuming the statement is true for the previous case, you assume it's true for all cases leading up to the current one. This is useful when the connection between cases isn't as straightforward as just the previous one. It's like proving you can climb the whole ladder by showing you can always jump up 2 rungs at a time.
Okay, so it's a more powerful tool for more complex situations. The book mentioned that induction is particularly useful for algorithm analysis. Can you explain how that works?
When you're designing an algorithm, you want to be sure that it will work correctly for any input size and that it will do so efficiently. Induction is a perfect tool for this. You can use it to prove that your algorithm will always produce the correct output and that it will do so within a certain time limit, no matter how large the input gets.
So it's like a mathematical guarantee that your algorithm is both correct and efficient. It sounds like induction's a pretty powerful concept.
It really is, and it's just one example of how these seemingly abstract tools of discrete math can have very practical applications in computer science and beyond.
All right, we've now laid some solid groundwork with proofs, sets, logic, and induction. But the source material also hints at something even more intriguing, the work of Alan Turing and the limits of computation. Can you tell us more about that?
This is where we start to push the boundaries of what's possible with mathematics and computing. Alan Turing was a brilliant mathematician who, even before the first computers were built, conceived of a theoretical model of computation, the Turing machine. It's essentially a very simple, abstract model of what a computer can do, but it turns out to be incredibly powerful.
Okay, so it's like the most basic, stripped-down idea of a computer. What can we do with this Turing machine?
Turing used his machine to explore the very limits of what computers can solve. He showed that there are some problems, even seemingly simple ones, that no algorithm, no matter how clever, can ever solve. These are called undecidable problems. This discovery was revolutionary. It completely changed our understanding of what computers could and could not do.
So even with all the incredible advancements we've seen in computing power, there are still problems that are fundamentally unsolvable. That's pretty mind-blowing.
It is. And while the specific problems Turing worked on might seem abstract, his ideas have profound implications for computer science today. They help us understand the theoretical limits of computation, guide us in developing more efficient algorithms, and even shed light on the nature of intelligence itself.
So it's not just about finding solutions, about understanding the nature of problems themselves and recognizing that some problems may not have solutions, at least in the way we currently understand computation. That's a pretty powerful insight. What's next on our agenda?
Let's shift from the abstract world of Turing machines to something a bit more concrete, but equally fascinating: number theory and cryptography. It might seem like a jump, but these two areas are intimately connected.
Okay, I'm curious to see how this unfolds. Number theory, that's all about the properties of numbers, right? Like prime
Yep.
numbers and stuff.
Exactly. The source material touches on key concepts in number theory, like prime numbers, the greatest common divisor, GCD, and modular arithmetic. These might seem like basic concepts, but they form the bedrock of modern cryptography.
I always found GCD a bit tricky back in school, but maybe seeing how it connects to cryptography will make it more interesting.
I think you'll find it fascinating. The source highlights the importance of relative primality when two numbers have a GCD of 1. This seemingly simple concept is at the heart of Euler's theorem, a powerful theorem in number theory with far-reaching implications.
Okay, but how does this all relate to keeping our online information secure? How do we jump from prime numbers to protecting our passwords?
This is where the magic happens. Modern encryption methods like RSA rely heavily on these concepts we've just discussed. RSA security is based on the fact that it's really hard to factor large numbers, especially those that are the product of two large prime numbers. Breaking the encryption would require finding those prime factors, which is computationally very expensive, even for supercomputers.
So the difficulty of factoring large numbers is what keeps our data secure. That's both incredible and a bit unsettling.
It is. It's a beautiful example of how abstract mathematical concepts can be applied to solve practical problems with enormous real-world impact.
Okay, so we've seen how number theory forms the foundation of modern cryptography. But the source material also mentions another real-world application of discrete math that I'm particularly curious about: Google's PageRank algorithm. This is how Google decides which websites to show us first when we search for something, right?
That's exactly right. PageRank is another example of how seemingly abstract math has a profound impact on our everyday lives. It's the reason why some websites appear at the top of your search results, while others are buried pages deep.
So how does it work? Does Google have little elves reading every web page and deciding which ones are the best?
Not quite. PageRank leverages the power of graphs. It uses something called the web graph, which is a directed graph where each web page is a vertex and the links between pages are edges. The initial idea was simple. The more incoming links a page has, the more important it probably is. It's kind of like a popularity contest.
So the more votes a page gets, the higher it ranks.
Yep.
That makes sense, but it seems a bit simplistic. Is that all there is to it?
That was the initial idea, but it quickly became clear that this approach had some limitations. It didn't account for the quality of the links. A link from a highly reputable website should carry more weight than a link from a spammy or irrelevant site. Think of it like recommendations. A recommendation from a trusted expert is worth more than a recommendation from someone you don't know.
Okay, so it's not just about quantity, but also about quality. How does PageRank incorporate that?
That's where the real ingenuity of the algorithm comes in. PageRank doesn't just count incoming links. It also considers the importance of the pages that are linking to a given page. It uses an iterative process to calculate the rank of each page, taking into account both the number and the quality of the incoming links. It's a bit like a recursive popularity contest, where your popularity depends not just on how many people know you, but also on how popular those people are themselves.
So it's all about understanding the network of relationships between pages, not just individual links. It's amazing how a complex idea like that can be captured mathematically and used to organize something as vast as the internet.
It is, and it's a testament to the power of discrete math to model and understand complex real-world phenomena. We've just scratched the surface in this first part of our deep dive, but I hope you're starting to see how these seemingly abstract concepts have profound implications for how we live, work, and interact with the world around us.
Absolutely. It's been eye-opening to see how these concepts connect and the unexpected ways they show up in our everyday lives. I can't wait to delve further into the world of discrete math in the next part of our deep dive. What do we have in store?
Next time, we'll explore even more fascinating applications of discrete math, including how it's used to model the spread of disease, analyze social networks, and even crack secret codes. We'll also delve deeper into the mind-bending world of infinity and explore some of the paradoxes and challenges that arise when dealing with concepts that are, well, infinite.
Sounds like we're in for another thrilling ride through the world of discrete math. I can't wait. Welcome back to our deep dive into the fascinating world of discrete math. Last time we explored some pretty fundamental concepts like proofs, sets, and logic, and even touched on the limits of computation with Alan Turing's work. I'm really eager to see how these ideas play out in real-world scenarios.
It's amazing how these seemingly abstract concepts have such a powerful impact on our everyday lives. Today, let's see how discrete math helps us tackle real-world problems in fields like epidemiology, cryptography, and even something as familiar as how Google ranks websites.
Okay, I'm all ears. Where do we start?
Well, remember how we talked about sets being these versatile collections of objects? Turns out they're not just mathematical curiosities. They can be incredibly useful for modeling real-world phenomena.
Really? Give me an example. I'm having trouble picturing how something as abstract as a set can be applied to the real world.
Think about the spread of a disease. You can represent the entire population as a set and then use subsets to track who's infected, who's recovered, and who's still susceptible. By applying set operations like unions and intersections, you can actually model how the disease might spread through the population over time.
Wow, so sets can help us understand and even predict epidemics. That's pretty powerful.
Exactly. And it's not just limited to diseases. You can use sets to model all sorts of things: social networks, financial transactions, even the flow of traffic in a city. Once you grasp the basic properties of sets and how to manipulate them, you can apply that knowledge to analyze a surprisingly wide range of problems.
That's really cool. It's like having a new lens to view the world through. What other surprises does discrete math have in store for us?
Let's circle back to Alan Turing and his work on undecidable problems. It turns out that his groundbreaking ideas have implications not just for theoretical computer science, but also for the very practical field of cryptography, the art of keeping secrets safe.
Okay, so how does Turing's work, which seemed pretty abstract, connect to something like protecting our online data?
The source material mentions a simplified encryption scheme that Turing actually developed during World War II. The idea was to encrypt messages by adding a secret key to them. Seems pretty straightforward, right?
Yeah, it sounds almost too simple. What's the catch?
Well, the source explains how this type of encryption, while simple, is very vulnerable. If the enemy intercepts multiple messages encrypted with the same key, they can use the greatest common divisor, that GCD we talked about earlier, to figure out the secret key. It's a classic example of how a seemingly clever idea can have a fatal flaw.
So the key to good encryption is to use a different key for each message. That sounds like a logistical nightmare.
You're absolutely right. That's one of the big challenges in cryptography, how to manage keys effectively. And that's where more sophisticated methods like RSA come in. They use a pair of keys, a public key for encryption, and a private key for decryption. The security of these systems relies on the difficulty of factoring large numbers, which, as we discussed earlier, is a problem that even powerful computers struggle with.
So even though Turing's original scheme had weaknesses, it paved the way for the development of more robust encryption methods that we rely on today. That's a great example of how even flawed ideas can be stepping stones to breakthroughs.
Absolutely. And it highlights the importance of rigorous analysis. In cryptography, even seemingly small oversights can have huge consequences for security.
Okay, we've seen how sets can be used to model real-world phenomena and how Turing's ideas influence modern cryptography. What other practical applications of discrete math should we explore?
Let's revisit Google's PageRank algorithm, which we touched on earlier. It's a fantastic example of how discrete math helps solve a real-world problem that affects millions of people every day.
Yes, I'm really curious to understand how PageRank actually works. It's fascinating how Google manages to sift through billions of web pages and present us with the most relevant results.
The source material reveals that the initial idea for PageRank was quite simple. It was based on the concept of in-degree, which is just the number of incoming links a web page has. The more links pointing to a page, the more important it was assumed to be.
So it's kind of like a popularity contest where pages with more links win. It seems logical on the surface, but is that all there is to it?
That was the initial approach, but it had some shortcomings. For instance, it didn't consider the quality of those incoming links. A link from a highly reputable website like a major news source or a government institution should carry more weight than a link from a random blog or a spam website.
Right, it makes sense that a link from a trusted source is more valuable than a link from a less authoritative one. How does PageRank address this issue?
That's where the more sophisticated version of PageRank comes in.
Hmm.
It doesn't just count the number of incoming links. It also considers the importance of the pages that are linking to a given page. It's like saying your popularity depends not just on how many people know you, but also on how popular those people are themselves. This is where the web graph, that network of interconnected pages we discussed earlier, becomes crucial.
So PageRank takes into account the whole network of relationships between pages, not just individual links. Sounds like a pretty complex calculation.
It is. PageRank uses an iterative process to calculate the rank of each page, taking into account both the number and the quality of incoming links. This process is mathematically elegant and incredibly effective at capturing the complex interplay of factors that determine a page's importance on the web.
It's amazing how such a seemingly simple act, like clicking on link, can contribute to this massive web of interconnectedness that PageRank then analyzes. It really highlights how discrete math can be used to understand and even manipulate complex systems.
You're absolutely right, and that's just the tip of the iceberg. We've only explored a handful of examples, but discrete math has applications in fields as diverse as computer graphics, artificial intelligence, and even finance.
Okay, my mind is officially blown. I'm starting to see discrete math everywhere now. It's not just about abstract theorems and proofs. It's about understanding patterns, relationships, and structures that exist in the real world.
That's a great insight. And it's one of the reasons why discrete math is so fundamental to computer science. Computers are essentially machines for manipulating information, and discrete math provides the tools for representing, analyzing, and transforming that information in meaningful ways.
So we've explored some incredibly practical applications of discrete math. But the source material also delves into some truly mind-bending concepts like the idea of different sizes of infinity. I'm both excited and a little terrified to dive into that.
This is where we enter the realm of Cantor's theorem, a revolutionary idea that challenged our intuitive understanding of infinity. Remember how we talked about cardinality, the size of a set? Cantor showed that not all infinities are created equal.
Wait, what? How can some infinities be bigger than others? Doesn't infinity just mean goes on forever?
That's what our intuition tells us. But Cantor's work revealed something much more profound. He proved that for any set, the set of all its subsets, called its power set, is always larger than the original set. This means that even if you have an infinite set, you can always create a larger infinite set by considering all its possible subsets.
So it's like an infinity of infinities to make my head spin a little.
It is mind-boggling. And this leads to the concept of uncountable sets, sets that are so vast that they can't be listed or counted even though they're infinite. The set of all real numbers is a classic example of an uncountable set. Cantor's work opened up a whole new universe of mathematical exploration.
So does this mean that some problems are just too big for computers to handle, even in theory?
That's a great question, and it's one that mathematicians and computer scientists continue to grapple with. We know from Turing's work that some problems are undecidable, meaning no algorithm can solve them. And Cantor's work adds another layer of complexity by showing that even for problems that are decidable, the sheer size of the solution space can be overwhelming.
So even with all our computing power, there are still limits to what we can compute. It's humbling, in a way.
It is, but these limitations are not necessarily a bad thing. They push us to be more creative, to develop more efficient algorithms, and to think carefully about the trade-offs between computational complexity and the value of the results we seek.
Okay, so we've explored some pretty heady concepts.
Yeah.
But the source material also brings us back down to earth with a discussion of water jug problems. Can you explain what those are and how they relate to discrete math?
Water jug problems are a classic example of how discrete math can be used to solve puzzles and optimize processes. Imagine you have two jugs with different capacities, and you need to measure out a specific amount of water using only those two jugs. It's a classic puzzle.
I remember struggling with puzzles like that as a kid. Is there a guaranteed way to solve them, or is it just trial and error?
It turns out there's a clever mathematical solution. As long as the amount of water you need to measure out is a multiple of the greatest common divisor, GCD, of the two jug capacities, you can always find a sequence of steps to solve it. It's a beautiful application of number theory to a seemingly simple problem.
So discrete math can help us be more efficient problem solvers, even when it comes to everyday tasks.
Absolutely. It helps us understand the underlying principles that govern many systems we interact with, from computer programs to communication networks to financial markets.
This deep dive is already exceeding my expectations. What else can we look forward to exploring in the next part?
In the final part of our deep dive, we'll delve into some of these systems in more detail, exploring how discrete math helps us design and analyze communication networks, optimize computer programs, and much more.
Okay, I'm hooked. I can't wait to see what other fascinating applications await us in the world of discrete math. Welcome back to the deep dive. We're on the final leg of our journey through the fascinating world of discrete math. It's been a wild ride so far.
It has been a whirlwind, exploring all the foundations of this incredibly versatile field. We've seen how discrete math can be, used to prove theorems, model all sorts of real-world phenomena, and even crack secret codes.
Yeah, we even explored the mind-boggling concept of infinity and delved into the power of sets, logic, and algorithms. I'm really excited to see what other practical applications we can uncover today.
Today, let's turn our attention to something you interact with every single day, probably without even realizing it. Communication networks. It might not be obvious at first, but discrete math plays a crucial role in how these networks actually function.
Okay, I'm intrigued. How does discrete math come into play when we're talking about things like the internet or phone networks?
Think about the internet as this vast web of interconnected computers. Each computer is like a node in this network, right? And the connections between them, those are like pathways for information to travel. This structure can be perfectly represented as a graph, a concept we've touched on a few times throughout this deep dive.
Right, I remember graphs from our discussion of PageRank. Each web page was a node, and the links between them were edges. So we can use the same idea to represent any kind of network.
Exactly. And once we have this graph representation, we can apply all the tools of discrete math to analyze the network's structure and behavior. We can ask questions like, how quickly can information travel through this network? How robust is it to failures? Can we even design it to be more efficient or resilient?
So by representing a network as a graph, we unlock this whole set of mathematical tools to understand how it works and even how to improve it. What are some of the specific things we can analyze using this approach?
One important concept is the diameter of a network. It's basically the longest, shortest path between any two nodes. Think of it as the maximum number of hops information needs to make to get from one point to another.
So a smaller diameter means faster communication, right? It's like finding the most efficient route on a map.
Exactly. Another important aspect is connectivity, which measures how resilient a network is to disruptions. A highly connected network has many redundant paths, so that even if some connections fail, information can still flow through alternative routes.
That makes sense. A network with lots of backup routes is like a city with well-planned streets. Even if there's construction or an accident, traffic can still flow smoothly.
That's a great analogy, and the beauty of discrete math is that we can actually quantify these concepts, like diameter and connectivity. We can use algorithms to calculate them, and then use this information to design networks with specific properties. Maybe we want a network with very low diameter, for super fast communication, or a network with very high connectivity to ensure reliability.
So discrete math isn't just about analyzing existing networks. It helps us create better ones. It's like having a blueprint for building optimal communication systems. Are there specific network designs that the source material mentions?
One fascinating example is the butterfly network. It's this highly structured network that's often used in parallel computing, where multiple processors work together on a single problem.
I've heard about parallel computing. It's like having a team of workers tackling different parts of a big project simultaneously, right?
That's a great way to put it. And the butterfly network provides a very efficient way to connect these processors and allow them to exchange data quickly.
So what makes the butterfly network so special? Why is it particularly well suited for parallel computing?
Well, it has some remarkable properties that make it very efficient. First, it has a very low diameter, which means information can zip between processors with minimal delay. Second, it has a beautiful recursive structure. This means it's built from smaller versions of itself, kind of like fractals. This recursive design makes it very scalable. You can easily build larger butterfly networks to accommodate more and more processors.
It's amazing how a simple recursive pattern can lead to such a powerful and efficient network design. It feels like discrete math is full of these elegant solutions that emerge from seemingly basic principles.
You're catching on to the beauty of this field, and the butterfly network is just one example. There are many other network designs out there, each with its own unique strengths and applications. As technology advances and we demand faster, more reliable communication systems, discrete math will continue to be an essential tool for network engineers.
So we've seen how discrete math is used in network design. Are there other practical applications mentioned in the source material?
One interesting example is the problem of register allocation in computer programming. It might sound a bit technical, but it's a crucial step in making computer programs run efficiently.
Okay. I'm willing to dive into the technical side of it. What exactly is register allocation?
Inside every computer processor, there are these small, super fast memory locations called registers. These registers hold the data that the processor is actively working on at any given moment. Think of them as the processor's workbench. It needs to have the right tools and materials readily available to work efficiently.
So the registers are like prime real estate in the processor's world.
Exactly. But here's the catch. There's usually a limited number of registers, and a program often needs to store many variables. So the compiler, which translates the program into machine code, has to figure out how to assign those variables to registers in the most efficient way possible.
Sounds like a tricky juggling act. How does discrete math help with this?
The source material explains how this register allocation problem can be cleverly modeled as a graph coloring problem.
Graph coloring, like what we do with maps to make sure neighboring countries have different colors.
It's the same basic idea, but instead of countries, we're dealing with variables in a program. Each variable becomes a node in our graph, and we connect two variables with an edge if they are live at the same time, meaning they both need to be stored in registers during a particular part of the program's execution.
So we're essentially creating a map of which variables need to coexist in registers at any given time. But how does coloring come into play?
The goal is to color this graph using the fewest possible colors where each color represents a register. The constraint is that adjacent nodes, variables that are live at the same time, cannot have the same color. This is because they can't share the same register.
Ah, that makes sense. So finding a way to color the graph with the minimum number of colors tells us how many registers we absolutely need to run the program efficiently. It's like finding the most compact way to organize the processor's workbench, right?
That's precisely it. It's a beautiful example of how a seemingly complex problem in compiler design can be transformed into a classic graph theory problem, with a well-established solution. Discrete math gives us the tools to solve these optimization problems in a systematic and efficient way.
I'm starting to see a recurring theme here. Discrete math is like this universal toolbox for solving problems across a wide range of domains, from computer science to network design to even epidemiology.
That's a great observation. It provides a framework for thinking about problems in this structured, logical way and equips you with a powerful set of tools for finding solutions.
So as we wrap up this deep dive into discrete math, what are some of the key takeaways you'd like our listener to remember?
I hope they've gained an appreciation for the beauty and elegance of discrete math. It's not just about dry formulas and theorems. It's a way of thinking about the world in terms of patterns, relationships, and structures.
It's about seeing the connections, the underlying principles that govern so many of the systems we interact with. It's like learning the secret language that unlocks a deeper understanding of how things work.
Exactly. And I hope they've also seen how incredibly practical this field is. It's not just a theoretical exercise. It has real-world applications that shape how we communicate, how we build software, and even how we protect our information online.
It's been a truly eye-opening experience to see how these seemingly abstract concepts can be applied to solve real-world problems and create innovative solutions.
And finally, I hope they've been inspired to explore discrete math further. The source material we've discussed is a great starting point, but it's just the tip of the iceberg. There's a whole universe of fascinating mathematical ideas out there waiting to be discovered.
So to our listener, we say, go forth and explore the amazing world of discrete math. You might be surprised by what you find and how it can empower you to think differently and solve problems more effectively.
And remember, the ability to think abstractly, to see patterns, and to reason logically is valuable, not just in technical fields, but in all aspects of life. It helps us navigate a complex world and make more informed decisions.
Thank you for joining us on this deep dive into the world of discrete mathematics. We hope you've enjoyed the journey as much as we have.
And until next time, happy exploring.